Hey kids, so now that you know how to predict the products of a double replacement reaction, you can go ahead and write net ionic equations. So net ionic equations are just showing which actual species are involved in the reaction itself. Because when we have a double replacement reaction, not everything's actually taking place and actually taking part of the actual reaction part, which is the making of the precipitate or the making of the water or the gas or whatever it is that double replacement reaction is actually making. So when you're initially writing and learning how to write net ionic equations, I want you to write 3 different equations. So what you're going to write is first your complete balanced reaction. Okay, so this is what you're already used to writing. You're going to write it out and you're going to balance it. Then you're going to write your net or your complete ionic equation. So what this is that you take each substance that is aqueous and you are going to separate it into its ions. If it's a solid, if it's a liquid, if it's a gas, you do not separate it because those do not separate into ions when dissolved in water, well, because they don't dissolve in water. Then you're going to write your net ionic, and what the net ionic is, you take everything that shows up on both sides of the reaction and cross those out because those are spectators. If you're a spectator at a soccer game or at a baseball game, football game, you're just watching. You're not actually participating in the game itself. And that's what these spectator ions are. They don't participate in the actual reaction. They're just kind of there. All right. So let's see how this looks. So with sodium chloride and silver nitrate, so first we're going to write our actual reaction that we're used to writing. So sodium chloride is not that, NaCl, and these are going to be solutions that we're starting with. So I should have put that in the equation, but I didn't. So NaCl aqueous plus silver nitrate, AgNO3. Remember, we're dropping and swapping to write our actual good ionic formulas. So what we just talked about in the predicting products video is we do outsides with outsides, insides with insides. So we're going to have NaNO3 as one of our products, and that's going to be aqueous because alkali metals and nitrates are always soluble in water, plus silver chloride. The silver comes first because it's the cation, and that's going to be solid because chlorides, even though they're usually soluble in water, silver is an exception. Okay, so let's take a look at this. This is already balanced. Now, before we actually draw out what's happening with our complete net ionic and then our net ionic itself, I want to show you why it is that we're doing these and why we have what are called spectator ions. So I'm going to draw a little beaker here. And I'm a fabulous artist, as you can see. Woo! So first I'm going to add in my sodium chloride. Now when it says aqueous, that means it's dissolved in water. So we know that an ionic compound is a positive ion bonded to a negative ion. And if it was a solid form, those two ions would be right smack next to each other, bonded together. But when they're aqueous, the water surrounds those ions and it pulls those ions apart. And it's still salt because we still have the sodium ions and we still have the chloride ions. So we're still going to have sodium and chloride in here. They're just not together. They have been separated by the water. Okay? The same thing happens with that silver nitrate. Because it's aqueous, the water pulls apart those two ions, and we're going to have Ags and NO3s. Okay? So when you mix these two things together, the silver and the chloride, because of the way they bond, don't dissolve in water. So when these two things get close to each other, they form an ionic compound. I drew these kind of far away, but I'm still going to circle them. So they form a solid, and they precipitate out and they fall to the bottom of the solution. That leaves your sodium and nitrate still just floating around in solution. That's why they're spectators. They didn't actually do anything. They're still going to be there present in the solution after the silver chloride precipitates and falls out. Okay, so spectator ions are anything that's still an ion after the reaction has taken place. Let me go ahead and erase my awesome drawing here. Sorry, I don't know why this is so crazy. Actually, it might just be faster for me to clear all of this and just rewrite my equation. Sorry about all of this. So after you get your balanced equation, oops, I had my sodium nitrate first. So after you get your balanced equation, and this one is already balanced, then what we do is we separate everything that can be separated into its ions. So that is all of our aqueous substances. So we have one sodium ion plus one chloride ion plus one silver ion plus one nitrate ion, yielding one sodium ion, one nitrate ion, and then solids, liquids, and gases do not ionize in water because the water did not pull those ions apart. So we would leave AgCl as that. Now to get from your complete ionic into your net ionic, you cross out anything that appears on both sides. So our sodium ions appear on both sides of the equation, and our nitrate ions appear on both sides of the equation. So that means the net ionic is whatever is left over after the spectators have been gotten rid of. So we have the chlorine still, we've got the silver still, and we have the silver chloride over here. Okay, and if everything is done correctly, this should still be balanced after you've done your initial reaction up there, okay? So let's take a look at this next example. We've got insides with insides, outsides with outsides. So we've got barium chloride, so BaCl2, and barium chloride is aqueous. Then we have H plus OH minus, so that is H2O. When you have hydrogen and hydroxide coming together, they make water. So we do have to balance this. We have to have two waters here. We're going to have two hydrochloric acids up there, okay? So, oh, and these are aqueous. Acids are usually going to be aqueous unless we state otherwise, okay? And we know water, in this case, is going to be liquid. So to get our complete net ionic then, what we do is we separate anything that's aqueous into its ions. So when we separate this hydrochloric acid here, we've got two hydrogen ions and we have two chloride ions, okay? When we separate this barium hydroxide, we have barium ion and we have two hydroxide ions, yielding the barium chloride is going to separate. So we have one barium ion and we have two chloride ions, okay? And then I've got two waters. That does not ionize because it's water and it's not going to separate into ions. Now, before we do our net ionic, we need to cross out any ions that appear on both sides of the equation because those are going to be our spectators. So we can see that the chloride ions pop up on both sides and the barium ions pop up on both sides. So that leaves us with two hydrogen ions, two hydroxide ions, and two waters. And that is how you do net ionic equations. So we would expect you guys to write net ionic reactions for double replacement reactions only. Okay, so if you have a double replacement reaction and it's asking you to do net ionic equations when applicable, you would do those for double replacement reactions. Okay, so give it a try. If you have questions, just let me know. Bye.